I built this, little two-stage feedback amplifier out of Molvino, his textbook. Just to try it out, I've always been kind of curious about amplifiers that do have a feedback between, the output of a two-stage or two or greater stage transistor amplifier. But he doesn't explain much to it. He's got this is like the end of the book, basically, or the end of this chapter. So he doesn't explain it very well. It spends like 3 pages on it. Well, 2 pages really. But anyway, it's a two-stage feedback amplifier, and I was, just curious to build it and see how it worked. Now he set this thing at only like 10 volts, and I decided to run mine at 15 volts. In fact, you can see it in the Falstat simulation over here, the exact component values I use. So, more or less, and it's close enough. On the capacitors and everything, it's, almost exact, except some of these are a little smaller than 10, but some of them are 10 microfarad. In fact, I may have used 10s across the board. I can't remember. No, I don't think I did. Let's see. Yeah, and that's 10, and I think this other is like, I don't know, 4.7 or something, for the output and input capacitors here. So that might be a little smaller, but 10's fine. So anyway, in case you wanted to build it yourself. But yeah, I was, wanting to, play around with it and stuff, just to see. And this amplifier, the only thing he discusses is how to calculate gain, okay? So, he's got gain, over here for the low end. You can see he's got a potentiometer right there, 10K potentiometer, and at that point you can set the gain up to 110, but as little as like 11 or 10 or 11, I think is probably, 10 really is a minimum gain. Now, one of the things about Molvino that I'm a little skeptical about is that, like in Hazen down there, he would use a factor in setting your bias chain, of saying, okay, whatever your base current that you calculate, which is, basically, you calculate you need, like, let's say you wanted this to be, 2 milliamps, we divide it by beta, right? So, it's like 2 microamps, but you'd use 10 times that, to set your, the current going through your voltage divider, so that it's, it's fairly stiff, but Molvino calls it firm when you do that. He recommends it be, 100 times that, okay, versus Hazen never talking about anything that stiff. But the one of the the nice thing about doing that is it does make your bias points even more stable, than Hazen, 10 times more, but 10 times more than what? I don't know. That's never quantified exactly, but I'm not sure exactly what the benefit is, but obviously you could compromise and do like 20 times or something if you're having some issues, but I've never really noticed any problems, doing it Hazen's way. So, but one of the drawbacks is that Hazen, if with these exact impedances, would be like 10 times this. So, instead of 2.2K, you'd be at 22K and then 100K there, for example. I'm not exactly sure how stiff he made this thing, but since that's his philosophy, I gotta assume he did, because these are still fairly low values compared to what Hazen would have used. So that's one of the consequences, basically, is that doing it this guy's way, you end up with 1/10 the input impedance, which usually, if you're dealing with a voltage amplifier, lower impedance is not what you want. You usually want higher impedance, input impedance. So anyway, that's something that I'm kind of wrangling with in this textbook, but that's okay. I'm just running with it for right now. But that was just a side note on this guy's textbook. But I built this thing. It looks like total garbage. I fucking hate breadboarding, and I particularly hate this one. I bend half the damn component leads I try to stick into this stupid thing, even using needle nose pliers to do it, which is almost mandatory. I think I got this free with some Arduino parts kit or something, some shit at one point in time. But at any rate, yeah, I got this rigged up, and you can hardly see the other transistor. It's like right over there. But yeah, it's quite the mess. But still, it produced enough interesting results to warrant a video. And like I said, you can see I got it running on Molvino, and I've got it set to. I'm looking at the DC bias points, and we'll do that here in a second. Right now I've got this thing set at 280 kilohertz at 160 millivolts input, and the gain I guess I got up to 100%. So, and I just did that. I don't have a pot in there. I just have a 10K resistor there, and that's in series with the the 1K resistor he has in his schematics, like you can see here. So basically, I'm running mine at 15 volts, and you can see 6 milliamps. And 6 milliamps is pretty much what 6.4 milliamps is what Falstat's predicting. And you can see the output here, because at 160 millivolts I got it, that's a sine wave, but I got it really saturated. I was trying to see what the maximum voltage swing on this is. And this is predicting, it's not predicting, it's saying it's about 10 volts. If you can't see this, it's too glowy, but, it's about 10 volts. That's about the maximum amplitude swing. So that's 2/3 of the supply voltage. So that should, in theory, give you an idea what your AC load line is, because, driving it both into cutoff and saturation, along the AC load line you start to clip your waveforms heavily. So, it gives you an idea what the maximum compliance is, and, because that's the one thing that's still not covered in these books is, how to actually design an amplifier for actual output swing, and I still not really determined any rules of thumb for that, because normally, when you're designing some kind of an amplifier, right, you have a few things you need to know, and one is what maximum input signal you want for your output to be, to go into your subsequent stage, whatever that is, an analog to digital converter or what have you. You want to know what the maximum undistorted voltage is going to be out of your device. That's what you're designed for. And then you want to know what kind of signal level you're trying to amplify. And then you got to work out how to go from your input signal of like 10 millivolts to 10 volts on the output, undistorted. Okay, what do you need to do that? And you may have to do multiple amplifier stages, but that's part of how in practice you would actually go about designing something like that in a lot of occasions. But these books never teach you how to do that, really. So there are no rules of thumb or anything developed, and that's why I was kind of looking at this, trying to determine a rule of thumb for it. And we later in the video are going to get to like looking at the frequency response of this thing too, which is some of the preliminary tests I did last night are intriguing. But yeah, I'm trying to look at it. So right now, again, I've got 160 millivolt input peak-to-peak signal, and our output is 10 volts. So let me adjust it now. Go down here, hit the amplitude, and let's adjust it down until it starts to look like a sine wave. And again, to do this properly, you want some kind of a distortion meter, obviously, because that looks like a sine wave visually anyway. So, I'm sure if it's probably like 5 or 10% THD at best, leaving the noise aside. And I'm going to make a little video about the noise in here. I spent some time trying to track it down, and I still am inconclusive about where some of this comes from. Because a lot of this jitter you're seeing is actually input noise coming off somewhere in here. Anyway, I'm going to make a little short video about that. later. But so we're at about six, about 7 volts here. So it would seem to be, interestingly enough, almost a 3 decibel thing, right? Almost, because that's like 70%, of what our maximum swing was. So I don't know, that's something that, I'm going to try to just kind of keep in mind as I do more of these things is, what it requires to do an undistorted input, versus maximum output swing, and again, that's probably going to vary, with a lot of different parameters. That, like I said, this is at 280 kilohertz right now, but so 70%, undistorted. So I wrote myself a note there. So 70% undistorted versus input. Again, something to kind of keep in mind. But yeah, I want to take a look now at the bias points here. So let me go ahead and switch our sine wave off. Alright, so we got essentially a DC condition. And let me try to set this up. So that maybe you can see some of the bias points and you can kind of compare them to what we're measuring on here, because I actually have not run this test yet since I put the right resistors in it. I actually had the wrong resistors in it last night. That still got interesting results anyway. Let's see. So basically, let's see what our let me look at this here. Okay, so right here, see, the base is the middle pin, and the emitter is the pin on my right. So let's just see what that is. Okay, so it's about 1.9 volts, and this is on the transistor I have my mouse cursor near. So, and that's predicting 2.1 volts, so it's pretty close, on this resistor or transistor right here. So let me look at the base voltage on that. This is right here. So it's measuring, about 2.64, and they say 2.7, so that's pretty accurate. I'm kind of testing the accuracy of Folstat here, because this thing actually, if you look at Folstat, I tried duplicating the same experiment, and I couldn't get it to go this high on a clipping waveform like we just saw in the scope. Okay, and let's see, the collector voltage is 8.12 volts, and this is predicting 7.6, so pretty decent though, close enough. And by the way, I did measure both these transistors, and both of them are in excess of 200, beta of 200, so I put 200 as my beta in each of these. That's as close as I can get without getting into craziness. Okay, so that's got that. Now let's see on the other transistor. Again, the collector output is 8.5 volts, so, and they're saying 8.2, so that's not bad. Let's see, because I was exploring the shit out of this stuff last night trying to figure out what I did wrong, and I just put the wrong collector resistors in it, because I had them mixed in the same bin, and so I thought they were 3.6K, but they're 5.6K. Duh. Let's see. So that's the collector. Let's see what the emitter voltage is if I can find it. There it is. Okay, so it's saying about 2.01 volts, and as you can see, 2.1 volts is what, is what Fallstat figures it to be. Now for the base, and working with breadboards sucks. I mean, just your test leads are gonna try to get some of those insulated clips or something, but they're so bulky. Okay, 2.7 volts on the input, and 2.7 volts is what it predicts. So yeah, I mean, Fallstat did good predicting the DC bias points. So let's turn the signal back on. Alright. Oh shit. This camera, so you didn't see any of that, huh? Well, this camera got distorted when I was probing it. Sorry about that. Okay, but at any rate, I read it off to you, so you kind of know what I was talking about. But basically, so yeah, I mean, that's pretty good signal level, but like I said, let me try to apply a signal on Fallstat here. And by the way, here's the link to this if you want to, let me see if I can make it. That's a link to a tiny URL, so, it'll get you to the circuit if you wanted to put it in yourself, in case I forget to put it in the notes, or the comments, or the, the description section down there below the video. Okay, but, so yeah, that's got us there, and like I said, you saw I had it clip at 10 volts, but like I said, with Fallstat, should really make this thing variable. I had it like 160 millivolts, right, when it was clipping. So, alright, it's clipping here too, but it's only giving us a, well, remember that's a max range, so yeah, I keep forgetting about that. Fallstat doesn't have a VP volt peak to peak, so it's actually pretty close to what my scope says. This would predict little over 9 volts, so that's not too bad. I mean, it's pretty close in terms of how the circuit simulates to how it behaves in reality, so it's alright, that's good. Okay, well now let's see, I had this thing. I'll go ahead and leave it at that level because it's no good. Well, let's look at that's what a square wave will look like in it right now at that same frequency. So again, you are still seeing some high frequency roll off there, obviously, where it's eating up some of the higher harmonics, or something similar. But the fact of the matter is that, for now we'll ignore the square waves, but we could reduce the amplitude. If you reduce the amplitude, and I guess I'll show you this, we're at 70, right? Okay, it becomes more and more square wave like, but there's still some rounding on it. But still, we're dealing with sine waves right now, so I'll just stick with that for these following tests for the moment. Alright, so let's take a look at, I'm going to decrease the frequency, and so you can see what remember 7 volts is what we're working with, peak to peak. Got it down to like 20 kilohertz, so we can kind of look at the low frequency response, but the voltage is still about 7 volts on it. Like I said, I wish this thing would focus better on shit like this. Anyway, but yeah, so anyway, I got it set at about 20 kilohertz, take it down to 10 kilohertz, and let me move my cursor over. Go down to 1 kilohertz. 200 hertz, 120 hertz. Okay, we've dropped a little bit, and that's because our input, all our capacitors are starting to, go into low frequency cutoff because they're basically acting like low pass filters. So I'm just trying to see if it, comes anywhere near the 3 decibel, 40 hertz level that I set it to, because we're down. Let's see, 70 hertz, 60 hertz, 50 hertz. So it should be around 5 volts or so, a little over 5 volts, which would be the 3 decibel point. So, okay, I went too far. Oops. Let's see, 20 hertz. I guess I'm too coarse. So somewhere around here is probably going to be the 3 decibel point. So, and that's about 32 hertz. So I guess I did the low end calculations pretty well on the filter caps. So that's not undecent at all. And like I said, at 40 hertz exactly, and it's at 5.7 volts. So, okay. Now let's go look at the other end. Okay, we got this back up to 10 kilohertz, and we're back up to our 7 volt setting from earlier. Alright, let's up this thing, 40 kilohertz, 100 kilohertz. Ah, shit. Hold on, this camera sucks. Let's see. Okay. Alright, still holding at about 7 volts for 360 kilohertz. Just starting to drop a little below 7 volts. But we're starting to see more distortion too. So just bear with me on it. Okay, so we're at 6.4 volts. Just hit 1 megahertz. Alright, 2.7 megahertz. Well, that makes me wonder. Yeah, 'cause you really can't see the gain. I might go ahead and hook Analog Discovery back up to it. I took it offline because I was trying to track down why so much noise is on this shit last night, and I was trying to eliminate it as a culprit, but I could benefit from my little gain measurement. I might go ahead and hook it back up and pause the video here for a second. Bear with me, because we're up to 2.8 megahertz right now, but it really helps having my little gain calculator on it. And I can still use this even with an external function generator. But yeah, the noise I was getting last night at first with this setup of mine, was god awful. I might go ahead and put my module back in place to run a test that hopefully we lower noise. Bear with me anyway. Okay, I got the Analog Discovery hooked up, and I put my old module back in it just to help reduce noise. Yeah, you can see right here, at this, same signal I had before I paused the video, we got a gain of about 22, and, at 2.8 megahertz, so, as you can see, as you can see there, barely, but, yeah, so, it's certainly heavily distorted like you see on the scope, but still it's at 2.8 megahertz. Now let me, switch our scope probe to 10x just to see what happens. Even though I don't think it's going to make that big of a difference at this frequency. Whoops, I think I switched the wrong thing. Okay. Yeah, I switched it to 10x, so let's see if there's any. Nah, still looks pretty much the same. I'll go ahead and leave it in 10x. So, prior to me doing that, we were at shit. About 1.7 volts, which is close to what the analog discovery says. But let me switch this back to. Man, this camera just gets on my nerves. Always pointed somewhere it shouldn't be. Okay, well, I'll switch it back to 10x. Okay, and so we're suggesting like 2 volts or something peak to peak. I kind of doubt that. Switch it back to 1x. You can see we're really 1.8 volts. Well, I don't know, how much you can, basically you can put some of these cheap probes. But let me go ahead and let's firstly, I had it at 70 millivolts, right? So let me go ahead and adjust that down, see if we can get what looks like a good sine wave. And yeah, at about 20 millivolts, we're starting to, see an okay looking sine wave, even at 2.7 megahertz, and it's about 900 volt peak to peak output. So let's see what happens, if we increase the frequency further. Now that thing you're seeing right there is actually external noise that's being fed into the system, because this amplifier is amplifying. Remember, I got this set to maximum gain. Now right now at this frequency, again, this analog discovery is still saying we have a gain of about 20, 25, something like that. And you can see that same, kind of glitch in there. And that's actually a noise frequency signal, and you can see it on the input too. That's external noise being coupled into this thing, coming from God knows where. But I got this thing down to 17 millivolts peak to peak input, so and the scope is saying our output is wish I could make this font bigger. Yeah, about 600 millivolts peak to peak at this input signal level. So, but at any rate, we're at 4.8 megahertz, so still with usable gain. I mean, a gain of 20 still. Let's go to higher frequency. Okay, we're up to about 6 megahertz now. Now it makes sense, definitely, to use 10x probes. On the analog discovery, it's saying our gain is about 15 still, though. I mean, we're still getting usable gain out of it. We're down to, 300 or 400 millivolts peak to peak on the output. But still, that's, it's actually usable gain. And it looks sine wave-like, no telling what kind of actual distortion there is in it. Okay, so up it to 20. Let's see how far we can take it. Okay, I got 260 millivolts I'm putting into it. We're at an output of about 1.7 volts peak to peak. It looks like that's about its maximum swing, again at full gain. And you can see on the analog discovery what we're doing. It's calculating a gain under the circumstances only 3x because its output's been fixed. So, in other words, we're well beyond what its maximum output swing is at 6 megahertz. Plus, the analog discovery is still in 1x mode too, so you got to take that with a little bit of a grain of salt. But let me go ahead and reduce it now to where we're well below clipping. Where I can start seeing the amplitude diminish. Okay, I'm starting to see the amplitude fall. Yeah, we're definitely. So we should be getting a more valid gain figure here. Again, even though it's attenuated, it's still a ratio. So you know, about a gain of 10 or 11. Now let's see what happens, you know, here at 6 megahertz while we're here. Um, if I reduce the gain, I'm going to cut the gain, you know, that resistor to less than 5 kilo ohms from the 10 kilo ohms it's set at right now, and see if there's any change in performance. I mean, it seems like it's about the same. So that's with it. Oh, well, I don't think it was plugged in. Man, God, I hate breadboards. Shit! I'm trying to do this with one hand is just next to impossible. Well, yeah, it doesn't seem to be making much difference. So between the two, but let me just short over it completely so we go down to the minimum gain. Alright, so that's its performance at minimum gain, which is pretty much the same. Its gain has dropped down to about 5 or 6 here. Here, hold on. Okay, get a closer view for you. So yeah, our gain is about, you know, 5 or 6 right now. Now let me disconnect it and see if anything happens so that we go back to full gain. Okay, gain of 11. So it does make a difference. But let's leave it at yeah, the low gain. But let's see. Okay, and like I said, remember these are 10x probes, so, well, no, yeah, I've got, well, no, what the hell? Okay, yeah, it's, you know, that's 10x mode, so this is saying 150 millivolts peak to peak and 10 with 10x probes, implying a 1.5 volt peak-to-peak output, which it could indeed have. Again, Analog Discovery is saying more like 1 volt, but it's got its probes are in 1x mode, and could go try to switch them both to 10, but then I'd have to change all my scales and everything. I'm not crazy about having to do that. Okay, now our gain's up to 20, 25. Again, so when I switch both the probes to 10x, but again, you're going to have to multiply the, I don't know if I can, yeah, I should be able to do that. Let's see, 10x, 10x, okay, shit, that looks like garbage. But yeah, okay, our gain's, you know, about 25 with a 3 volt peak to peak, it's saying, on the output. So again, that would kind of correlate with what this is saying, you know, this assuming 10x, you know, about 3.7 volts. But again, I don't know which has the better probes, because all these probes are pretty cheap. But still, to produce that kind of gain, again, this at full gain setting, it's supposed to be a gain of 100, but of course we're not seeing that here. But you know, but to have it to be at 25 is still usable gain. And let's see, let me try to adjust this. But still a distorted sine wave, you know, as you can see here. Let me try to reduce the amplitude a little bit, because that's not as distorted. And our gain is, you know, still about 24, 25. Now, volt peak to peak would be about 2.5 volts according to this. That's, again, the best I can do. I mean, I'm feeding with a 50 millivolt signal. All these digital function generators have range limits on them. Like Analog Discovery, I think, can only go down to really 0.3 millivolts or so. So, you know, when you're at 1-bit resolution, you know, on the waveform, if I remember correctly, it's pretty low. So even if you're doing, you know, set to 5 or 10 millivolts, you're not actually getting that many vertical samples anymore. So, you know, you got to keep that in mind, what its bit resolution actually is. So, but at any rate, you know, that's this thing working up to 6 megahertz and still producing usable gain, albeit highly diminished. Now, let's leave it this same signal level and see what happens as I start to reduce the frequencies. I guess, I still prefer going to to 1x probe so I can set it to a lower attenuation. You get less jitter noise. I can up the signal level typically, but so let me leave the signal level the same, and let's start decreasing it, below 5 megahertz, and right now we're at 300 millivolts peak to peak, and again, 10x probes, keep that in mind. But about 0.3 volts peak to peak, is what this is saying. And again, multiply that roughly by 10 for the actual voltage. So, Analog Discovery is saying that peak to peak output under the circumstances is about 2.5 volts peak to peak. Let me change the signal to where we can get a better view of the waveform itself. Shit, stupid camera. It keeps getting pointed up compared to where I'm holding it. But yeah, it still roughly looks sine wave-like. I can't say much for the input, but it still looks roughly sine wave-like, and our gain's up to in the neighborhood of around 30 or so. So right now, and that's at 4.6 megahertz. So let me go ahead and remember the 300 millivolt thing. Alright, 3.7 megahertz. Okay, our signal strength is definitely gaining now. We're up to 370 millivolts times 10. And let me reduce this a little bit. See, now we're up to 450 millivolts. So, signal strength is definitely de-attenuating. Now we're to half a volt. And see, that's all that fucking noise I'm talking about. I don't know where the fuck that's coming from. I've spent several hours trying to track it down last night and still couldn't really determine where it's coming from. But we're at 2 megahertz or 200 kilohertz now. So 100 kilohertz. 80, 40, jittery. That fucking noise signal right on that tends to cause some jitter. We're about 500 millivolts now. So, going back to the Analog Discovery over here, let me adjust it. Okay, so it's saying our gain's about 50 now. So the gain has definitely changed, and the voltage peak to peak is 4.5 volts according to this. So it's definitely changed, and our frequency is about 30 kilohertz right now. So, it shows you that this thing does actually still produce usable gain out to 6 megahertz, but it's not going to be steady. Your signal will attenuate, and so forth, the higher the frequency, like you'd kind of expect. And I actually wanted to experiment with this amplifier originally because I wanted to, these emitter bypass capacitors that are rather large here, I wanted to see if I could put like some, mylar or other capacitors, polypropylene, in parallel with this, that would handle it at the high frequency end, because I was kind of wanting to, actually put some of these on the network analyzer on the Analog Discovery and see what their frequency response range, because I'll bet you this is well beyond their, their transition point where they start becoming behaving like inductors instead of capacitors, meaning their impedance will start to increase. I was thinking if you put another capacitor in parallel, that could operate, like a, couple of hundred nanofarad or something more practical, you know, that it might take over where this leaves off at high frequencies, because this is one source that will start to attenuate it, because as these start to go away, your gain starts to fall. You know, because right now the gain's really high on this output stage. You see here, um, let's see, you know, so these are my figures, which are, you know, a bit off, but yeah, I don't remember if I calculated the gain on this or not. But at any rate, the gain would be, you know, this, you know, if this capacitor didn't exist, the gain would be 1K pretty much divided into 3.6, so it'd be, but really it's, yeah, it's about right. You know, there'd be about a gain of 3 on this. And this, you know, without this capacitor, you know, would be, you know, even a little lower. But then, of course, you got your feedback circuit. So, but as those capacitors become and start to behave more like inductors, their impedance increases, right? So as a result, it's in effect like the resistor is coming back into the equation. So, you know, it's reducing your gain. So it's like if I could take and put a bypass cap here, maybe even here, because again, he didn't specify any of this capacitor, so I'm not clear what size capacitor I should use here, so I just use the same one, as you see in my little, you know, my Volstat over here. You know, I just used the same one that I used everywhere else, but I was like, yeah, if you put a bypass on each of these, it might improve the high frequency response, maybe. Because I mean, these transistors are 300 megahertz transistors. They're, you know, 2N, you know, 3904s. So, you know, you should be able to get a higher range really out of them. You know, than we're seeing here. So, especially if you have the gain set to minimum. So, now let's see what happens, by the way, when I do that real quick. All right, so I'm going from a gain of, you know, like 50 right now. Let me bypass that. Alright, so now our gain's down to about 7, or 6 or 7 when I hook the alligator clip across that. So basically, anyway, you know, I can probably up the signal level now, especially at this low of a frequency. We're getting higher output, so up to 200 millivolts still looks like a sine wave. Yeah, still looks like a sine wave. Output voltage is about 2.3 volts. Gain is about 10 now. It's about 9, so it's closer to what it's supposed to be according to the book. So now we're starting to clip right now at about 350 millivolts input. So let me go below that a little bit. Okay, so you know, yeah, our gain is 10x, down about 2.3 volts peak to peak output. Now let's try another waveform. Huh, square wave looks great. You know, we're only at you know, like 30 kilohertz, but you know, the square wave looks great. Start to up it. 120 kilohertz. Got some ringing in there, which I'm surprised the damn thing doesn't ring like a bell with all this inline inductance I have with all these stupid component leads on this thing. Yeah, we're up to 300 kilohertz. Still looking halfway decent, like halfway decent square wave. Still stick that into a digital logic circuit basically. But our voltage is still 2.7 volts. Let's see. Oops, wrong damn way. Alright, so we still got a gain of about 10. So you know, so at least up to 400 kilohertz, it certainly doesn't look too bad. 500, 600, certainly showing some rounding. 800, and 1 megahertz, and yeah, a little rounded, but still definitely demonstrably a square wave. So I don't think any digital circuit would actually have a problem with a square wave with that going in. It's got some, again, low end ringing, but a lot of that's probably because of this mess here, this bird's nest I built. Increasing it to 1.6 megahertz. Alright, it's rounded, but it's still an acceptable square wave. You could actually use that in a digital logic. Most square waves, if you ever actually probed, a lot of digital circuitry, especially older stuff, you'll end up with square waves that look like kind of like that all the time. Again, it's got a lot of lower level ringing, but it's like I said, about 2.6 megahertz. It's still a usable-ish sine wave. It's just its timing's going to be off though. But it's starting to shark fin on us. It's starting to look more and more like a, not like a square wave anymore, but like a shark fin. So you can even see that on the Analog Discovery. Remember, I still got all my probes set at 10x. So, but again, it's 2.8 volts peak to peak, but, I'll still bet you could feed this into digital logic circuit and still get, reasonable communications with it. Again, especially if you built this thing up and didn't have quite so much ringing in it. But that would help better, but even as it is, remember, this is AC-ish waveform, though, right now, because I got to come out of a capacitor, but still, you can fix that. Anyway, so that pretty much, takes a look at this rather interesting little amplifier, and, like I actually did, with this amplifier, when it had the wrong resistor values, and I was using this, you wouldn't believe all the fucking noise that was on this thing. I'd never seen noise that bad. But still, I was able to generate a network analysis, gain analysis here on the network analyzer, and it's, at gain of 11 across the board until about 1 megahertz. I'd never, in all the amplifiers I've built so far, I've never got this good of a gain profile, without it starting to fall off. Most of them were like 400 or 500 kilohertz. So, when they should have been higher. And there weren't 2 stages, there were 1 stage, but this still produced interesting enough results where I thought it was worth making a video over. Because this certainly does produce usable gain, well into the, low megahertz range, So, anyway, I don't know if you found that useful or not, with all the camera issues, and probably quite seasick by now, but anyway, that ought to cover it. Cheers. Wait, before I go, switch, that's the square wave mode, right? I wanted to go ahead and switch to sine wave mode just to see what that looks at this particular frequency at this particular setting. So it's kind of shark finish. You can even see that on the Analog Discovery. It's kind of shark finish. But let me, I still got the amplitude set to, 270 millivolts. So let's start reducing that until it looks more sine wave-ish. Okay, so that's, looking like an okay sine wave. It's about 170 millivolts. Remember, our gain, I still got it shorted out, so we got minimum gain on it. Analog Discovery is saying the gain is about 9 or 10, so which is what it's supposed to be, even out to 2.9 megahertz, like we got it right now. So let's go ahead and change back over to a square wave at that same level. What the hell? Oh, God damn it. Okay, so that's what a square wave looks like at that same level. It's only, it's still about 2 volts peak to peak and a gain of 10 or 11. I don't know if that's, it's certainly less shark finish. So, at least has some flat top on it. Let me reduce it further to 130 millivolts. Now we're starting to see ringing on the top for sure, very definite. So, but at 110 millivolts input. You can see what it looks like on the Discovery. So analog Discovery, that is. So anyway, but if you keep increasing it, the more you increase it, the more sharp finish it becomes. So but I mean, at some point, you can still get good square waves. So it's kind of a matter of output swing, as you might expect. So the lower the output swing, the lower the distortion, on your amplifiers typically. So even with feedback like this, and let's take it off, up to full gain. Now we've really sharp finned. So the gain's back up to like 36 at 2.9 megahertz. So anyway, like I said, we'll probably leave it at that unless I think of something else before I hit stop. And also, I thought you might be just interested for shits and giggles to take a look at some of the different waveforms this function generator can generate on this output here. So, square, triangle, CMOS, half wave, rectify, full wave, rectify. Let me adjust this. Alright, it's DC. Okay, this is half wave. That's step wave, full wave, step wave, reverse step wave, noise, logarithmics, pulses, weird sine wave looking thing. It's fun to look at. And then this thing. And that's an arbitrary waveform. And by the way, this thing could save arbitrary waveforms. I don't know what people were talking about. The thing you had to load arbitrary waveforms on this thing every time you booted it up or unplugged it. Well, I put this on there like 2 months ago. I moved it all over the place without power. So, so that's total horseshit. Anyway, that's kind of just thought you might be curious about it to, look at that for, shits and giggles. Back to a sine wave. Cheers. Oh, and by the way, I turned the frequency down for that too, just to clear everything up. So we're not at like 2 or 3 megahertz anymore. It's like 600 kilohertz. So, and quarter of a volt input. So anyway, just wanted to be clear so you weren't confused about that. Okay, one last thing I wanted to cover, and I'm glad I took some time to think about it first, is that I did make a previous video to this where I made, used the wrong resistor values. Now you remember all the tests we went through, testing this thing out to really high frequencies. I did the same thing last night, but with the, instead of 3600 ohm resistors for the, for the collector resistors, I used 5600 ohms by accident. But it did produce some interesting results that I showed in that video that, I got almost uniform amplification out to 6 megahertz, at, with a 5x gain or something like that, but it was almost uniform. It was interesting, so I might actually edit that video. It was only a 30-minute video, but it produced some interesting results, so I might edit out all the embarrassing bits, since I didn't realize I had the wrong resistor in there. But just, put those results. So I might, I might put a link to it, down in the description of the video. And another thing I just did, I went ahead and hooked the Analog Discovery's waveform generator back up to this, so I'm not using that anymore. And the scope right now is not generating a signal because I wanted to run another signal analysis on it. And this one I did out to 10 megahertz, and you can see it's virtually, it's got virtually flat gain. None of the amplifiers I have tested have ever showed this kind of uniform gain to them. And again, Analog Discovery is really a 5, maybe 10 megahertz instrument, so it gets more dodgy the higher the frequency. But let's go ahead and try it at a higher frequency. I'll do it to 25 megahertz. Let's just see what happens here. I set the 70 millivolt signal level, so that should be safe based on the experiments we ran. So, wow, it doesn't start crapping out until, certainly well after 10 megahertz. as we just established. So it's interesting, but again, you can't count on the analog discovery so much this low. But none of the amplifiers, all of them had roll-offs well below 1 megahertz. This is the first amplifier I've seen produce gain constantly and consistently, across the board. Again, remember we got our oscilloscope probe set to 10x still, so you're gonna, they're gonna be less of a factor than they normally are when I run tests like this, but they should still be good for 4 to 6 megahertz. But 10x, you should be good for a lot higher. But yeah, so that was interesting. So yeah, I decided to rerun that test. So, by connecting analog discovery fully up to it again. So anyway, it's just interesting results that I thought I'd share. I'm considering the possibility of building this into a perf board and then running some more tests. I haven't made up my mind if I want to do that or not, because this would take up a lot of perf board, all these damn capacitors. But I would like to see if the frequency response is even better with all these lead links trimmed short, you know what I mean, and soldered in place as opposed to being on a perf board. To see what the difference is. Hell, maybe perf boards are better than circuit boards, but with all the capacitance between the traces and shit, I would be skeptical about that, but that would be a curious test to use the exact same components in it. So now that I got that issue from last night resolved, it might be worth doing it now that it's actually functioning properly in output voltage swing wise. But yeah, that one I did last night, it had a much lower bias point because it was only about 4 volts for the DC Q point. That's why I went through and measured the Q points to check them now. So it was, its Q point was set a lot lower, but it was producing some really, at the right input signal level, it's producing pretty much uniform response, very little drop, clear out to 6 megahertz. And, which I didn't quite get that, here because the amplitude started increasing a lot. That wasn't happening in the tests I ran last night. So again, I may put a link to it if I do edit that video at some point, and so you can check that out if you're interested. But it'll be way shorter than 30 minutes if I edit it down. It's certainly way shorter than this one. So anyway, this is it. Final video, final cut. Cheers.